Okay, we got our final on Wednesday. Now, I don't have your last test graded yet. You can come by Monday and pick it up. I'll be in here from 8:30 to 12:30, so I'm usually in here anyway, so that's kind of my office anymore. But I should have them graded and ready to hand back to you Monday. Today, we'll talk about what to expect on the final, and, well, you probably expect this already, but I will allow a sheet of paper, front and back. I guess I should specify 8.5 by 11, 8.5 inches by 11 inches. Get my units on there so I'm not counting off anything. I don't want these big old poster boards up, and I know you guys would try that. So there'll be lots of formulas for you to put down, I'm sure, maybe even a few examples of different problems, but today we'll kind of go test by test and remind you of what we've done all semester. We've made a long way, and you've learned a lot. Well, some of you have. So, with test 1, we started out evaluating limits, and what we ended up doing with most of them, that fancy L'Hopital, almost looks like L'Hospital, but now the thing to remember there, to use L'Hopital's rule, we have to have either 0 over 0 or infinity over infinity. There's a lot of indeterminate forms that we worked with that would not work on L'Hopital's rule, so we had to do some algebra to rewrite it to where L'Hopital's rule would work. But I think you guys remember L'Hopital's rule. It's just some of the details of getting it into the form that we needed in. And some of the problems involved your e to the natural log of whatever, or, another way is take the natural log of y and the natural log of the expression. For example, I'll show you what number 8 was a limit as x approaches infinity, 1 plus 1 over x to the x power. Well, this can be done in, like I said, a couple different ways. We do have the indeterminate form of 1 to the infinity, but we can't use L'Hopital's rule in that form. So what Professor Berger showed was we take e to the natural log of this, and then basically we work on the exponent. And what I showed, a little bit different, let y equal this, and then take the natural log of both sides. So either way, it's a slight difference. The main part of it will be working with the natural log of that to the x power, which first thing we need to do is pull the exponent out. And then as we think x to approaching infinity, well, here we'll have infinity times 0. Another indeterminate form, but still not a form we can use L'Hopital's rule. What do we need to do to change it to where we can use L'Hopital's rule? Okay. Change x into, well, it's easier when you say it the way you said it, but technically it's 1 divided by 1 over x, and then times the natural log. Basically turns into this. And then from there we can go through the derivative, and our L'Hopital's rule, take the derivative of the top, derivative of the bottom, and let's see. Derivative of the top, we'd have 1 over the inside times the derivative of the inside. Now I'm just going to put that as the derivative of 1 over x, because what's the bottom? Well, it's the derivative of 1 over x. Of course, you'll probably go ahead and work through that. Negative 1 x to the negative 2, but that would cancel with this, and we're left with just this part. So as x approaches infinity now, this goes to 1, but remember, we're not, this is this part right here, or this part right here. So whichever direction you go, this one's a little more direct, we end up with e to the 1, or natural log of y equals 1, so y would equal, well, again, e to the first. So now you'll probably get, the more math you have, the more you'll automatically recognize this as the number e. This is the definition of e, but this is why this approaches e. Okay? So logarithmic, I guess, manipulation is a good way to put it. We looked at using logarithms when we take derivatives as well, or if we have the next page on the test 1, we looked at find the derivative, and we had several special functions. Now, some of those special functions were logarithms of different bases. So make sure you have formulas for calculating log, like number 9 log base 3, number 10 log base 10. Okay, it's not just the natural log, but it's related to the natural log. And then both of those, we could simplify the logarithm using properties, log properties, before you take the derivative. It makes life a lot easier. Okay. And then not just the logarithms, but we also looked at the inverse trig functions, derivatives of those in this chapter, the fun hyperbolic functions. Those actually turn out pretty nice, but make sure you know the formulas there. And then there are some functions that we have to use logarithmic differentiation, like number 14, sine of x to the x power. To find that derivative, we've got to change it to a logarithm. We can say y equals this, and then natural log of y equals the natural log of sine x to the x. And then again, log property, bring the exponent out in front. And then using technically implicit differentiation, take the derivative of both sides with respect to x. Derivative of natural log of y with respect to x is 1 over y times dy by dx. And then take the derivative of this, product rule, go through all that. And then dy by dx will equal y times the derivative of all that. So logarithmic differentiation gets it's involved, but we have to use it sometimes to be able to use our derivative shortcuts in the forms that we have. So, and then the last part of test 1, finding antiderivatives, and these are your like your inverse trig functions, the antiderivatives that end up giving us the inverse trig functions, e to the, those were all arcsine, arctangent, arcsecant. Now, you do have the one sheet of notes available, but I will have copies of the integral tables also, so you don't have to worry about, well, you may have to worry about finding where the integral formula is, but you won't have to worry about writing down those formulas. I'll give you this sheet. This is from the ThinkWell material. I think you guys can access that online if you want to, but I'll have paper copies of that for you for the final. Okay, test 2. We looked at all those fun integral techniques. How to find the integral of, well, cosines and sines and tangents, and using trig identities. Okay. We also looked at partial fractions. Now, let me just say, on these types of problems, I will say something like, show your work. So that means do not just find that in the integral tables. Now, you may want to find it in the integral tables to make sure you're right, but you need to show how you get these. There will be some integration that I will allow you to do the tables, but there will be a few problems from this unit where I will say, show your work. That means don't use the tables. So, but the ones there, trig identities, and that's more the cosine and sine, cosine squared, sine squared, how they translate, tangent squared and secant squared. Okay. Also, we looked at partial fractions, changing a big ugly fraction into several little fractions that we've added together. Partial fractions. Integration by parts. Trig substitution. And those are more, if we start out with the square root of x squared minus 4, or 1 over, or something like 9 plus x squared, that would be a good trig substitution. Again, using those trig identities, but that's definitely something you'll want to write down, which substitution for what type of integral. And then one kind of combination integral, maybe going back to partial fractions, number 6 on test 2, you actually had to do long division to rewrite the form of it before you integrated it. And then it turned out 1 plus this fraction, and then you were able to do partial fractions on the fraction part, but not from the very beginning. So anytime you have the degree in the numerator the same as the degree in the denominator, or if it's bigger than the degree in the denominator, you can rewrite the function using long division. And then from there, that usually simplifies it down to where you can integrate it or maybe use one of the techniques. And then the very end of this test, estimating definite integrals using trapezoid rule. Make sure you know how to do that, trapezoid rule or Simpson's rule. That's just making sure you have the right formula down and make sure you can find the correct x values over the interval. So, any questions on test 2? Okay, then test 3, we got into using integration in working through some applications. Well, the first part of it was actually improper integrals. And that, we talked about how do we calculate some integral that goes off to infinity. Okay, well, basic idea there is change it to a limit. Then from 1 to b is a definite integral. Go through the fundamental theorem with the definite integral and then apply the limit. Now, there was another type of improper integral. That's where f of x is not continuous over a to b. Like, well, number 2, we had 1 over x minus 3 quantity cubed over the integral from 0 to 4. Why would this be an improper integral? Okay, not continuous at 3, so what we'd have to do, split it into 2 parts. And then this one we'd have to do the limit as b, well, not approaching infinity, but b approaching 3 from the left. And then this one, the limit a approaching 3 from the right. We'll have 2 different parts, 2 different limits to do on that improper integral. Okay. So that was kind of the first part. Number 3 was average value of a function. And as easy as this one is compared to some of these others, you probably want 3 or 4 of these, but that's your 1 over b minus a, and then integrating from a to b of f of x dx. Then we looked at several ways to calculate the volume. A surface of revolution. Take a curve, revolve it about x-axis, y-axis, x equals 3, y equals -2, something like that. And calculating the volume, you can either use the disk method, or the shell method. Now, most of these, both methods would work. One method would be easier than the other, but it depends on the setup, which one is easier. But be able to do both ways and figure out which way is the easiest for the particular region we're generating. That was 4, 5, and 6 out of test 3. Next application, arc length. And then surface area kind of came directly from arc length. But again, a couple formulas that you'll need to write down. And then the last couple of applications, work, basically your force times distance, and we looked at the spring, the work a spring does, the work done in launching something, some cargo from the Earth's the Earth's surface up into the atmosphere, so many miles or whatever. So work, force times the distance traveled, and make sure you're able to set up the appropriate integration there. And then the last one we looked at was center of gravity or center of mass. And there again, that's your X bar, Y bar, and the formulas for those. X bar was the A to B of X, f of X dx. Now the denominator is actually the mass. We worked with almost always the constant density. Density times area represents mass. And what happened is, if it's a constant density, we'd pull it out front. Well, that's the same function we'd be integrating. So constant density factored out both ways cancel out. So it basically turned out to be the area in the denominator. Then in the numerator, we had x times the f of x, or I guess region between two curves, it was f of x minus g of x. So, and then y bar, this one got a little more complicated with the formula, changing it all into terms of x. We had integral from a to b, well, that's the numerator, 1/2 of our top function squared minus the bottom function squared dx, all over the area. So this right here kind of became the key to setting up the problem, and then the numerators just slight differences from what the area integration turned out to be. Okay, so lots of good applications on test 3. Any particular problems, questions on those? Next we had sequences and series. And, well, make sure you recognize whether we're talking about a sequence or a series. And we didn't do a lot with sequences, but we do need to understand the different terminology there. Then the main parts, whether a series converges or diverges, and state the test used. That will be part of it, not just take a guess and say, well, it converges. Well, how do you know? So go through the details like we did on test 4. A couple problems, couple tests, we could say exactly what it converged to. That was with the geometric series. And which other one? The telescoping. Both of these, if it converged, we could say it converges to this particular value. And then the geometric series, we can use it to change a repeating decimal to a fraction. That's a possibility on the final as well. And that was, what, problem number 4 on test 4? Okay. So separate it out into a series of fractions and then simplify it down to the geometric series format. And then you can calculate A over 1 minus R for your converges to this particular value. Now the very last part of test 4 dealt with not only convergence, but is it absolute convergence or conditional convergence? And those were mainly working with alternating series. So make sure you're able to figure out, is it absolute or is it conditional, or perhaps maybe the original diverges. But that wouldn't be interesting if it was divergent from the beginning. Okay, and test 5, that'll be real fresh in your mind, but conic sections, make sure you have formulas down, standard form of the equation for parabolas, ellipses, hyperbolas. Go through all those details. Parametric equations. Some of the main things we looked at there were derivative and second derivative. Make sure you're finding or know the formulas for the derivatives. And then what we can do with the first derivative, that's slope of the tangent line. We may need to find where we have horizontal tangent lines or vertical tangent lines. We may need to see where a function is increasing or decreasing. Or second derivative, we can see where a curve is concave up or concave down. Okay. So be able to sketch the curve of, I'll make that one a fairly straightforward one, but sketch a curve given parametric equations, forgot about that, and let's see, derivatives. One more thing with the parametric equations was the arc length. Find the arc length of a parametrized curve from one point to another point. So make sure you have that formula down. Next up was polar coordinates, and we kind of finished out the rest of the unit on that. convert back and forth from rectangular to polar or from polar to rectangular, points, equations, and then finally some calculus with polar coordinates. Find the slope of the tangent line, and then find the area of a given region, or maybe inside one and outside another, or something between two curves. But slope and area, derivative and definite integral work there. So, any questions on test 5 or for the final in general? Overall, I think, if I remember right, there's 15 questions. So a little bit more than our typical test in here, but not much more. So 20 questions I think would still be a little too much. I do want you to get done Wednesday, so.